Welcome to video 8. In this video we'll finish up making this C# component. So let's jump right in. Let's open back up our C# script. So we just made a function that will take in a list of parameters along with a curve, and it returns a list of points on that curve specified by those parameters, very similar to the evaluate curve component in Grasshopper. So let's continue to practice making functions, and let's make another function just below this one. This function is going to give us the distances between our points. It's going to measure the distance between one point and its neighboring points. So we're going to measure the distance from point 0 to point 1, from point 1 to point 2, and so on, all the way around our curve. So to define a function, first we need to write public, and this is going to be a list of distances, and distances are going to be numbers, so we'll type list double, because we need a list of doubles coming out. And then we get to define or to name our function. Let's call it find distances. Next, we need to define the inputs for this function. So all we need for an input here is just a list of points. Point 3D, and then we just need to name that so we can use it when we're defining the function. Let's call it plist. And then we need curly brackets, and we will define our function in between these curly brackets. The first thing we need this function to do is make a new list, a list of doubles, a list of numbers, and we'll call this distances equals new list of doubles. Remember the parentheses and a semicolon. So this is going to be what we return. We return this new list. So whenever we call the find distances function, it's going to give us this list of distances. And so we can skip ahead and write return just so we don't forget, and then copy this here. We want to return the distances, but right now this is empty. So we need to tell the function how to find those distances. And so we're going to do another version of what we did up here. This is a for each loop. We're just going to do a for loop, and this is the more common, the more frequently used version of this. And so instead of typing for each, we're just going to type for, and then again we have a parentheses, and then we need to initialize an integer. And to do that, we just type int, and so int is telling the C# component that we're making a new piece of data, and it's going to be an integer, and then we need to name that integer, and usually we just call this I for loops. This is called a for loop that we're making right now. So we're making a new integer, let's call it I, and let's set the value of I at first to 0. So that's a whole statement. We just made a new integer, we called it I, and we set its value to 0. And since this is a full statement, we need a semicolon. But that's not all we need for the for loop. We need to tell it how many times we want to, or how large we want that integer to go. This might be a little bit confusing at first, but we really do use for loops all the time, and in no time at all, because you'll be doing this over and over again. This will make perfect sense, and it'll just be second nature. Anyway, there are 3 things we need to do inside these parentheses. The first is make a counter. The second is set a limit on that counter, essentially telling it when to stop counting. So we can say I is less than, and assuming we're counting up, we'll put an upper limit on I, and this is very important. If we forget to do this, it will count forever, and then we'll have to close Rhino because it's literally stuck in a loop. So we need to define a stopping point for this for loop, and that stopping point is going to be the length of this list that we're putting in. And so let's copy this. So now we have list, and to get the length of that list, the number of items in that list, we call something called count. So we say plist.count with a capital C. Count is a property that lists have. It's an integer that says how many items are in the list. And so what this expression here is saying is find this list and count how many items are in that list, and this is just that number. And so if there are 13 items in that list, then this expression equals 13. This just says 13. So this would say I is less than 13. And then we need one more thing, so that's statement 2, but we need 3 statements. Our third one is every time we run through this for loop, how do we increase or how do we change the value of I? So what we want to do is tell it to increase I by 1 each time. And so the most explicit way to write this is to say I is equal to I plus 1. And we don't need a semicolon there, actually. So what this is saying, and remember this equal is a little different than what you're probably used to as far as equal signs go. This is saying, first find what is I plus 1 equal to. And we set it equal to 0, I equal to 0 first, and so 0 plus 1 is equal to 1. And so it's going to take this value here, which is now 1, and put it into I. And then it's going to do the loop again, but it's going to start with I equals 1. And then it's going to go through, and 1 plus 1 is 2, and so the next I is going to equal 2. And the next I is going to equal 3. And it's going to keep increasing until it hits I is equal to 12. And it's not going to go beyond that because we told it to stop when I is less than 13, if this list is in fact 13 items long. If this list was 7 items long, then the last number it will run is 6, because 7 is not less than 7, and so 6 is going to be the last one. 7 is equal to 7. So this is saying keep doing this until the middle statement is no longer true. If this middle statement is true, do it again. But as soon as I is no longer less than the number of items in this list, then stop the for loop. And the reason we're only doing less than and not less than or equal to is because we're starting with 0. And so the first run through is going to be I equals 0. And the last run through is going to be, let's say there are 13 in here. The last run through is going to be I equals 12. And that's what we want, because even though there are 13 items in the list, remember when we start with 0, the last index in that list is going to be 1 less than that full count. And so if we write list.count, I equals less than list.count, then it's going to end at the right value. And so this is the long way to write this. Normally we'll just write I plus plus. That's just like the shorthand, because this is so common. And it's so common to want to increase a value by 1 each time you iterate through it that there's a shortcut, and you can just write I plus plus. And so for I equals 0, I is less than the count of the list, and I plus plus, what do we want to do? We need our curly brackets again, and it's going to do something, whatever we tell it to do in between these curly brackets. So the first thing we want it to do is make a new point. So let's define a point, 3D, and let's call that, or no, we want it to make a new double. We want it to make a new number. So a double, and let's call that double new distance. And that double is going to be equal to the distance between point 0 and point 1. And these points are coming through our point list. So the first run through is going to measure the distance between these 2 points. So the way to do that is to first grab the first point in this list. So let's copy this. And then to grab the first index, we make these square brackets, and then we tell it what, so this is saying get index item, whatever we put in here. And so we want to start by getting index item 0, but we want this to change every time. And so instead of writing 0 here, we're going to grab I, because right now on the first run through, I is equal to 0. So we grab the list, and then we grab index I from that list. And so now this represents a point, the first point in our list. And then we say we're going to call another function, and this is the distance2 function. So we write dot distance2, and then we need to tell it what distance we want to measure. Like we want to measure the distance between this point and what other point. And so we're going to write that in between these parentheses. So let's just copy this. And if we put that in there, it's going to measure the distance between the first item and the first item, which is going to be 0. But we don't want that. We want it to measure the distance between the first item and the next item in the list. So we can do I plus 1. And that's going to say when this is 0, then this is going to be the first point in the list, and this is going to be the second point in the list. I plus 1 is the index 1. So we can do that, but there's going to be a problem when we get to the end of the list, because we'll run out of index items before we get to the end of this for loop. And it's going to give us an error and say something about the index must be in range. So instead of doing it this way, let's redefine this for loop as starting at 1, and we still want it to go to the end of the list, just like this, but instead of measuring the distance from the first, right now this would actually be the second item. So instead of measuring it from an item in the list and the next item in the list, let's measure it from an item in the list and the previous item in the list. And so if we start at 1, then we can take 1 minus 1, and that's going to give us 0, and there is an index 0, so that's fine. And then when we get to the end of the list, when we get to item 12, if there are 13 in here, that's going to be the last item in the list, and it's going to measure to item 11. So point 12, what's the distance between point 12 and point 11? So that's a way to ensure that we don't overstep here as far as index numbers go. That's the problem that you'll run into all the time is when you do a for loop and you're defining which items it's supposed to be looking at. A lot of the times a mistake you'll make is trying to grab an item that's actually not within that range. Anyway, so what this is saying, that this is just telling us that this new number, this new double, is this distance. And so we need to take that new double, that new distance, and add it to this new list that we just made. So let's copy the name of that list, distances.add new distance. So each time it's going to add another item to this list of distances. And each time this new double we made will get erased and then created again. After it's done doing everything in there, it's going to do it however many times there are items in the list, and then it's going to return the distances at the end. And so when we call the find distances function, it's going to return those distances. So I'm just going to click OK to make sure I didn't make any mistakes. And since it's green, that means we're still good. So let's go back up here, and we can make a new list just to test this out. List double. Oops, see, it auto-corrected that, and I didn't want it to. So list double, let's just call it D for now, or D's, equals new list double, parentheses, semicolon. And so let's say D's equals, call this find distances, and the list of, then we need to give it a list of points in here. And the points are gonna come from this list that we got in the find points from the find points function. So that's the only input here. We just have a list that we need to input. And now it's going to give us out a list of different distances between all of these points. And so to test this, let's plug the distances. Instead of parameters in here, we'll put the distances in here. And so now coming out of B is going to be a list of distances, okay? And so now we have the distance between all of these points. And you can see that, so these are close, but they're not exact. And they should be exact since we have a circle here. But this is due to some rounding by the parameters that we're using. These parameters are only going to 5 decimal places, and so there's going to be some discrepancy here. But let's check and see what the distances are for this component, the one that we used at first, and these should be exact, the distances between these. And so I'm going to get a shift list component, and what this is going to do is shift the list in one direction by one value, and so index 0 will now be index 1 and so on. So the default here is 1, and that's fine. And so I just want to measure the distance between this shifted list and these points here. So I'm going to get a distance component and plug that into B and that into A and see what the distances coming out here are. Okay, and so these are all the same, which is good because this doesn't round at all when it's doing this, or where it rounds is much deeper into the decimals. And there's really no reason to get these numbers from this component. We could have used a range component, or if we wanted to have more precise numbers, we could have divided the number 1 inside our C# component, divided 1 by however many divisions we wanted, then multiplied that number by our division steps. But this parameter output was conveniently just sitting right there, and it doesn't really matter anyway, since the point of this component is to make these distances all equal each other, and this component will work for all of the surfaces that we have. So if we go back and plug in the triangle surface, we can see that the divide curve component gives us points with pretty big range between the distances. Our component will bring that range to 0. So you can see that the distance between these points here is only 1.8, where most of them are 2.8. So that's where it's wrapping around an angle here. Okay, so that's fine for now. So let's go back into our function and let's make another function. And this one will be the most complicated function and the function that actually moves these points each time it runs. I'm actually going to go back out here and hide all of these for now. Okay, so let's define our next function. This is also going to return a list of doubles. This time, this is going to be our updated parameters. And so let's call this update parameters. So this new function is called update parameters, and it is going to take in our current list of parameters. So a list of doubles. Let's call that pars. It's going to take in our curve, our input curve. So curve. Let's call this in curve. And it's going to take in a weight, which is a double, and we'll call that W. And if you remember, one of the inputs was weight right here, and that's what this is referring to. Then we need our curly brackets, and inside those we'll define what this function does. So the first thing that this function is going to do, or we need it to do, is make several different lists. Actually, 4 different lists. The first one is going to be a list of doubles, a list of numbers, and that's going to be our new parameters. So we can call that new params equals new list. New list of doubles. The next one is going to be a list of distances, also double. We'll call these dists. And parentheses, semicolon. We also need a list of distances, but this is going to be distances that are normalized based on the length of the curve. So it doesn't matter what kind of curve we put in there, we want it to normalize that full length to 1. And so the distances we also want in that same scale. So this is also going to be a list of doubles, and we'll call it norm dists for normalized distances. And the last list that we need is going to be a list of points. So list point 3D, let's call this new points, new list 3D, parentheses, semicolon. So now we have 4 new empty lists. We also need to find what the actual the actual length of the curve is, whatever the input curve is, because we're going to divide all the distances by that to get a normalized distance for each space between each point. So we need to make a new double, and we do that by typing double, and we'll call this curve length. And that is going to be equal to our input curve, and we're going to call another function called getLength. And this function doesn't take in any arguments, like these don't have to either. This is just going to calculate the length of this curve. And so this number over here is going to be put into this variable that we just made and specified as a double. So next, let's set our, actually I'm going to call this new pars, because we have our incoming is a list of parameters that I called pars, and the updated parameters we're calling new pars, so that it's just easier to follow that way. So let's set new pars, Control C, Control V, equal to pars. So to begin with, our new parameters are just equal to our parameters. We'll change that in a moment here, but for now we need it to find our initial points. So we also need to find the points where they would be according to our input parameters. And so we'll set new points for now. And now we're going to call, so down here, since we defined this function first, we can call it down here. So we're going to call this function find points, and it takes inputs, it takes a list of parameters, and it takes a curve. So our list of parameters, we're going to use our new parameters. And we could use this also, it doesn't matter, either one, because at this point they're identical. They will change. But for now, our new parameters, and it also takes in a curve, and that's our input curve. So now these points are wherever they would be according to the initial parameters. And next we need to find the distance between these points. And so we know how to do that. We've done that before. We just need to call this find distances function. And these are going to be our initial distances. So in this list, we want that to be equal to the find distances. We'll call this function. And the inputs is just these parameters, or just these points that we just found here, new points. So the find distances function takes in a list of points, and it gives you a list of distances between those points. Remember the semicolon here. And next we're going to do another for each loop. So for each, and this time we want to normalize these distances. So for each double, because this is a list of doubles now. We made it up here, we made a list of doubles. So for each double, and then we need to name the variables. Let's call them dis. So each dis is short for distance here. So for each dis in dists, which is our list. So for each number, so for each distance in our list of distances, we want to do something. And we want to, so we have our curly brackets because we're going to define something that we need to do for each distance in the list of distances. We need to divide this distance. So I'm going to copy this and say divide by the curve length. And that's going to be a double, and we'll call that norm dis equals. So now I just made a new double, a new distance that is our original actual distances, the actual units, depending on how far apart each one of these points is from its neighbor. And I divided that by the actual length of the curve, and so that's going to give us a normalized distance between each one. Since the little nudges we're going to give these points will be to their parameter values, the adjustments to their position will be in units relative to the length of the curve if the length of the curve were 1. Because of this, we want our distances between the points to be in units that also reflect this. So that's why we want normalized distances. And so this is the value that we need to put into this list that we made up here called norm dists. And so I'm going to click on this and say copy and paste it down here, .add. And so each time it goes through this loop, we need to add this double to this list that was empty, or this list up here that we made an empty list, and we need to add all of these new values to it down here. So now this list is populated with all of the normalized distances between each point, and that's all we need to do for that for each loop. And so this next step is going to be the most important this is kind of the step that defines the entire C# component. This is like why we're making it. And it might be the most confusing also, but it's very short. So I'm going to make another for loop. And this time for int I equals, normally we would write 0, but now we're going to write int I equals 1. Actually, in this component, we've only done int I equals 1. So we're going to start at 1, and we're going to stop counting at the length of our new parameters list minus 1. So I is less than new parameters dot count minus 1. We actually want 1 less than the number of items in our new parameters list. And the reason for that is if we look at this triangle here, this is point 0. Okay, let's do this. So this point is index 0 and 1. There are actually 2 points there. You can only see one, but they're on top of each other. So this also represents 2 different parameters. This represents parameter 0, and as we go all the way around, this represents parameter 1. And we don't want to change these parameters at all. We want to keep these exactly as they are. And so that's why we're starting at I equals 1. We're starting at this one here, and we're going to this one here, 1 less than the total count. So that's why we have new pars.count minus 1. We're only going to change these locations. These are exactly where we need them to be. And then we'll do I++, whoops, a capital I plus plus, and then our curly brackets. And next we need to define how we want these to move. So if you remember earlier I said imagine that these are agents, these have some agency, or we can give these some kind of rules so that they move according to their basic surroundings. So what these are going to do, each point, let's start with this point, let's say that this is point 1. It's going to measure the distance it is away from this point, and it's going to measure the distance it is away from this point according to the normalized distances. So it's going to look in that list, and we can just imagine that it's judging how far it is from this point and judging how far it is from this point. And then whichever distance is further, it's going to move a little bit in that direction. So here, it's this point here will measure this distance, and it'll measure this distance, and it will notice that this distance is further than this distance, and it's going to move a little bit in this direction. So let's create a new double, and we'll call this difference. And this is just going to be equal to the difference between the distance to the point in front and the distance to the point behind. So we're going to find the distance between the point in question, whichever point we're on in this iteration, and the point in front of it. And when I equals 1, the first iteration of this loop, that distance is the number at index 1 in our norm dists list, which is the second item in that list. And then we subtract from that number the distance to the point behind the point in question. So again, when I equals 1, that number is stored in norm dists at index 0. So we'll be subtracting the first item in that list from the second item in that list. So second item minus first item. So to generalize this to every case for I, this is just norm dists index I minus norm dists index I minus 1. So let's write that down. We have norm dists I, copy that, but instead of I, we write I minus 1 in here. So let's check the last iteration in this for loop just to be sure. We asked this for loop to keep I less than the number of items in our new pars list minus 1. So we have 13 items in our new pars list. You can count 12 points here, but there are 2 at the point on the right. The first one and the last one are just on top of each other. So there are 13 items in the new pars list. Minus 1 is 12. So right now this statement says I is less than 12. Keep I less than 12. So the last I in this iteration will be 11. So when I equals 11, and since there are 12 normalized distances in our norm dists list, this is also equal to norm dists.count minus 1. So anyway, when I equals 11, this loop will take norm dists at index 11, the last item in that list, and subtract norm dists at index 10, the second to last item in that list. And we're taking the distance in front of the point in question minus the distance behind, because that will give us a positive value if the distance in front is bigger, meaning that the point will have to move forward. If the distance behind is bigger and the point should be moving backward, we'll get a negative number. So that way we don't have to worry about positive or negative, forward or backward. That information is just stored in our distance variable. Positive means forward, negative means backwards. And then we want to add that difference to the parameter. So this is parameter 1. So let's get our parameter list and say I. In this case, this is parameter 1 equals, we're going to set it equals to itself plus this difference. And not just this difference, we're going to set it equal to itself plus this difference multiplied by our weight. So we can adjust how much each move is. So again, if this distance is negative, then it will move backward a little bit. If the distance is positive, then this point will move forward a little bit. And we'll adjust how much each move is by adjusting our weight. And that's all we need to do. So we need to remember to return something. So what we're returning is our new parameters. So now this update parameters will be equal to our new parameters. It's going to go through this list each time. And when I say each time, I mean each time we call this function. We're going to put this function in a for loop and run it multiple times, each time fine-tuning the position of each point a little bit by fine-tuning the values in our parameter list. So that's all we need to do for the update parameters function. And then we just need to call it up here in the run script part of the code. Okay, so we don't need this anymore. This was just to check and see what the distances were. And so we're going to make another for loop up here. Int I, and this time we are going to say int I equals 0. I is less than, and that's why we have the iterations input, if you see here. So the C# component automatically makes this whole line up here. And so the iterations is going to say how many times are we going to go through and fine tune these distances. So copy that. I is less than iterations and I plus plus. And then we need to call the update parameters. We want to run this function as many times as there are iterations. So grab this, Control C, and remember that this is outputting a new list of doubles. And we want that to be our parameters list. And so let's type parameters is equal to update parameters. And this function that we just defined takes in a list of doubles, a curve, and a weight. So it takes in the initial parameters that we had. So it's going to take in this list that we made at the beginning. And so here this is a little bit helpful. It just told me what the next input it's expecting was, which is a curve. And so in curve is going to be our curve. And then last, it's going to be a double, which is the weight. And we have that here. That's the weight that we put as an input here. That's going to go directly into this. And so once we've run this function, each time we run it, it's going to update the parameters list. And then that parameters list is going to go into the function again, and then it's going to update it again. So this is going to be like a loop, just updating itself each time for as many times as we put as we define the iterations integer. And so I'm going to click OK, and hopefully, okay, I made a mistake somewhere. Let's see what this says. DS does not exist. Where did I write DS? Line 74. Oh, okay, since I deleted this part that was distances before, so let's just put parameters there. We don't need to have parameters. We don't need to have parameters as an output. What we're looking for is the actual points, and we do need to update the points. So now that we have a new list of parameters, let's find the points again. So points equals find points in actually all of this. So we just did the exact same thing here that we did up here, but the difference is code always runs like from the top line down. And so at this point, parameters is different. It's just the in parameters. And that's what we started with here, but it updated it this many times. And so now parameters is different. And so the points are going to be different. And so our output is going to be based on these new parameters here. Okay. And that worked, and we iterated 100 times because that was what we started with as our iterations number. And these look a little better. Let's check to see what the distances are. And we can do that. I'm going to delete these for now. So the points are here, coming out of A. And to check to see what the distances between the points are, and to make sure that they're all the same, we could just make this information in the C# component and pull it out as another output. But instead, let's do this on the Grasshopper canvas. Let's get a shift list component. And again, this is going to shift the list up 1 and a distance component. So this is going to tell us the distance between this list of points, which is the same list of points but adjusted by 1 index, and this list of points. So, and let's see what the outputs are. Okay, so this last index is measuring between index 0 and index 1, or parameter 0 and parameter 1, which is the start point and the end point. We don't want to actually measure that. That's only going to matter when this wraps around. It won't matter, so let's go back and plug in the flat one. Oh, I guess it would, yeah, it definitely will matter. So it'll matter either way, but we just don't want to measure that. So let's go do call index, and I'm going to get a panel, and I'm going to type -1 into that panel. So -1 in Grasshopper is basically, when you're talking about a list, the -1 index is always the last item in the list. And that's what this is referring to, true. And so if I turn this to false, it wouldn't know what to do with -1, but I think that's true. Let's see. Yeah, so it doesn't know. But we wrap it, and so it's true. And so if you ever want to get the last item in a list, it's going to be the -1st index. And so if we plug this in, then all of these numbers are going to be the same. That's no surprise since we started with the flat one. But let's start with the referenced surface. And so all of these are pretty close. We can do something else to, let's sort this list. There's another way to evaluate how well this is working. And so now this is sorted, this list has sorted it from the smallest distance between the two and the largest. And so let's get list item. The first item in this list is going to be the shortest distance, and the last item is going to be the longest distance. So if you remember just a second ago, I said the last item is -1. The first item is always going to be 0. Let's plug both of these in. So 0, then I'm going to hold shift and -1. And so that's going to give me the first item and the last item in that list. So this is the smallest distance, and this is the longest distance. If I get a dispatch component, this is going to separate the list according to a pattern, which is true-false by default. All that means is since there's 2 items in here, one's going to come out of A and one's going to come out of B. And then I'm going to use a subtraction. And just to show what's going on here, I'll copy these and make it a little bigger so we can see. And if we want, let's just do this absolute value, because it doesn't matter which one's bigger. Okay, so the difference, the biggest difference here is 0.08, and so that's not bad. If we increased the iterations, this should get smaller. So let's go, where are we here? So we're using this referenced curve here, and these are our points. So you can see them moving a little bit, they're just slightly adjusting. And so we increased from 100 to 512 iterations, and now the distance is much smaller, which makes sense because it's fine-tuning every iteration. So let's get the triangle. Let's try it with the triangle. Okay, so it's a really tiny difference between these. Okay, so that's good. That's all we need for the C# component. That's making sure that every line between each point is the same distance. So now we have all the points to make the lines that will be the bottoms of our squares. In the next video, we'll just clean this up a little bit and then array points on our surfaces that will be the corners for our squares.